there any questions? Let me make sure these are all. Any questions? Okay. So I'm going to try today to basically, well, I'll start with a little, the end of chapter 5, which is a sort of hand-waving discussion of E plus E minus goes to mu plus mu minus. So let me just, I think this discussion is just meant to suggest the flavor. So what we've got is E plus E minus photon mu plus. Well, actually, I've got everything backwards. The convention is this way. In other words, the negatively charged leptons are thought to be the leptons, and the other one is the anton. In other words, when we plug in when you get the electricity out of a socket like that, you expect electrons, not positrons. Okay, and we're in the so-called CM frame. Yes, it's the Carnegie Mellon frame. Anyway, in that frame, the total momentum, of course, is, total free momentum is 0, and the zeroth component of the four momentum is E1 plus E2. And so the energy carried by the photon is K, and so K squared is just E center of mass squared. And then, and so 1 over K squared is 1 over E center of mass squared. On the other hand, the matrix element, mu plus mu minus, whatever this thing is, E plus E minus, well, this is going to have a square root of, and we're going to have 2E1, 2E2, 2E3, 2E4, but each of these is E center of mass, so this is E center of mass squared. So effectively, the 1 over K squared cancels the final state factors, and well, I'm leaving out, of course, the M. And so altogether, this matrix element Fmi has a 1 over E center of mass squared, all these factors, and so in fact what you get here is factor 4 times whatever the spin contribution is. And here we're going to be very casual. Well, there's also a factor of E to the 4th because of the coupling constant. You have an E here and E there. And so in the matrix element, it's going to be E squared. And now the spins. What are the spins? Well, the incoming electron has a full momentum that is basically E 0, 0, E. If it's moving in the Z direction, E2 is E 0, 0 minus E. And now, what do we have? We have these, we can think of these electrons as having spin 1/2 in the direction of motion or opposite the direction of motion. If you have 2 in the direction of motion, you get spin 1. You have 2 in the opposite direction of motion, you have spin 1. But if you have something like this or that, you get spin 0. And so, actually that's not entirely true because there are clutches that I'm ignoring. But anyway, so this is actually very, very sloppy. polarization vectors of the photons that these guys can couple to are E1, 0, 1, 0, 0, and E2 equal to 0, 0, 1, 0. Here we're thinking of this being T, X, Y, Z, and so we're imagining that the angular momentum of the electrons is either fully in the z direction or in the anti-z direction, and so it couples to photons that are also, let us say, we're imagining they have a momentum in that direction, and so their polarization has to be like that. And on the other hand, the final state polarizations for the photons are, one of them can be in the x direction like that, but the other one is cosine theta. Well, let me get the other. The outgoing momenta for the muons are P3, P4, and these are E1, 0, and now we're saying sine theta, cosine theta, and this one is E1, 0 minus sine theta minus cosine theta. And so we're imagining that the momentum of the final state photon, or the photon that couples to the final state particles, has a momentum in this direct angle theta with respect to the z-axis. And so we're ignoring phi because we're invoking some azimuthal symmetry. The hands are waving rather fast here, okay? So this is, take this with sort of a grain of salt. So the photon polarizations have to be parallel and perpendicular to these two guys, and so this particular one, this second one here, is it can be cosine theta, but it has to be minus sine theta. So then this started into that gives 0, and all right, so what we get then is for one amplitude, we have, if epsilon 1 is the first polarization vector, then we have epsilon 1 bar plus epsilon 2 bar epsilon 1, and this epsilon 1 bar, that gives you a 1, but epsilon 1, epsilon 2 bar gives you a 0. And so this is in fact minus 1 because of Schwarz's metric. And 2, on the other hand, is epsilon 1 bar, epsilon 2 plus epsilon 2 bar, epsilon 2. And here's epsilon 2. Epsilon 2 into epsilon 1 bar is 0. Epsilon 2 into epsilon 2 bar is cosine theta, and the minus sign, so this is minus cosine theta. So altogether, what we get is 1 plus cosine squared theta, and altogether the cross-section turns out to be d sigma d omega melon equals 1 over 64 pi squared E center of mass squared times 1 plus cosine squared theta. So that's the leading order cross section. Let me, since this has been sort of sloppy, let me just say something about photon polarizations. If we imagine we're in the Coulomb gauge, which is the most physical gauge for electrodynamics, then what we have is we have del dot A equal to 0. And that says that the 3 momentum dotted into the polarization vectors has to be 0. And for each momentum, there are 2 polarization vectors. Y has to do with special relativity. I hope we'll get to that in a nice way in a later chapter. The other is that when we quantize electrodynamics in the Coulomb gauge, we have Gauss's law, which tells us that del dot E is rho. And in the Coulomb gauge, del dot E, well, del dot hitting A is 0, and hitting A dot is also 0. So this is effectively minus Laplacian A0. And I better put a plus or minus because I'm not keeping track of the sign. So A0 is a dependent variable when you quantize in the Coulomb gauge. And A0 then is just some integral over rho, and so then there's no A0 in the theory anymore when you quantize QED in the Coulomb gauge. So consequently, epsilon 0 is 0. So the polarization vectors for a photon in the Coulomb gauge, there are 2 possible polarizations. It's a 3x3 rotation matrix that takes the z-axis into the p direction. Divide by square root of 2, and you act on these vectors, which are the polarization vectors for a photon of momentum in the z direction. And these are 0, 1, plus or minus I, 0. And I think we've switched here to, I don't think it matters. Weinberg, I think, makes this the energy variable, the energy position, and then this becomes the x position. Oh, then it does matter. All right, so we're thinking of this as the time x, y, z. All right, so that's the picture. And plus is I think right circularly polarized, so the angular momentum is the direction of motion. And so those are the 2 polarization vectors in the Coulomb gauge. And so I thought I'd write down something in this discussion that was actually rigorously true as opposed to the movement of the air. Does anybody have a question? All right. Okay, the next topic is the LSZ reduction formula. LSZ stands for Lehmann, which of course went bankrupt in 2008. Zemanzik and Zimmerman. That's a joke. Not the physicist. So what is this reduction formula? It's FSI is the product over initial states, and let's use label J, of I integral d4th xj e to minus I pj xj. That's the Lorentz inner product. Box J plus m squared times then the product over the final states. In fact, it would have made more sense to put the final states on the left. All right, let me do that. Final states on the left, and then I change that to a plus. Initial states here. Okay, so there's all of that. And what is it acting on? What it's acting on is a Green's function. And what we're thinking of here is the physical vacuum, as opposed, in other words, the vacuum of the interacting theory. See, we don't know a hell of a lot about. Right? time-ordered product of all the fields, phi of x1, phi of xn, vacuum of the interacting theory. Okay. And these are the fields. This thing, vacuum time-ordered product of fields, this is called the Green's function, named after Green. So it's Green's function, and he somehow, having invented the mathematical technique, he has been given possession of all the functions of that form, so they're called Green's function. I remember when I was a graduate student, I had no idea why people were calling them Green's functions. I didn't know of the mathematician Green or physicist Green. And I thought, well, it can't be the color green. So they wouldn't use the apostrophe S, and of course some people didn't use the apostrophe S. It was very confusing. Okay, now, what are we thinking of in this scattering? What we're thinking of is that interactions occur only for t greater than minus big T, less than big T. So in early times, the particles, in fact, let me do it Weinberg's way, in which, by the way, let me just mention the difference between the Schwartz book and the Weinberg book. The Schwartz book tries to make everything as accessible as possible and to cover the whole standard model and a lot of topics in modern quantum theory. Weinberg, on the other hand, tries to tell everything as precisely and correctly and rigorously as possible. And so, if you're confused by something in Schwartz, look it up in Weinberg. I think that's where I pulled this out of. Okay, this is a 3x3 matrix, or if you want 4x4, but it doesn't have that. Okay, well, in Weinberg's view, Weinberg has time going up, and I think that makes a little more sense. So we've got these asymptotic particles, say particle 1, particle 2, coming together, and we imagine that they're simply moving as free particles. They're not interacting. Of course, it's plausible because they're macroscopic distances apart. And then there's some scattering that we're trying to understand. And then in the far future, we have these various final state particles going out. And these are also behaving as free particles when they get out of the interaction region. So we have here time t, everything here is free. We have here time minus t, everything down here is free. So, and then here we have the interaction. Okay? So simple plane waves, mystery or complexity, simple plane waves. That's the picture. Okay. Now what's happening with these box plus m squared operators is they are basically going to be canceling poles of the form m squared minus p squared. All right, and what we expect, of course, from this expression there is that this thing will give us something like a d sigma, or we'll be able to compute d sigma, and we were interested in basically two particles going to many particles. So relative velocity, matrix element squared, and d Lorentz invariant phase space, so d ellipse. And remember that we have, I'm trying to use as much board as possible.
It certainly makes it interesting.
Well, it's once you start erasing, everything gets cloudy. So S minus the identity, this is going to be I, that's the fetish factor. 2 pi to the 4th, delta 4 for total energy conservation, energy momentum conservation, and then the matrix element. And of course, the initial state, let's see, there's a little bit of green here. The initial state is going to be square root of 2e1, 2e2. Creation operator for P1 at minus t, or minus infinity if you want, AP2 of minus t dagger, and those are acting on this physical vacuum, omega. And then the final state would be square root of 2e3 dot 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 2en a dagger P3 big T dot 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 a dagger Pn T omega. All right, so that's the picture, and we're going to be assuming that all the P's 3 through n are different from P1 and P2, just to make things simple. Those are, otherwise it's kind of trivial. Now, one way of doing this calculation is to say that the operators A of t have the form e to the I h t a of 0 e to the minus I h t. This would be, they would then be Heisenberg picture operators, Heisenberg time dependence. Now, what Schwartz does instead is give them a Schwartz picture time dependence. And in the Schwartz picture, this T only refers to the interaction. And on the other hand, the time dependence is just e to the plus or minus I omega t, or IET, the free field time dependence of this operator. He shoves that into factors like this. Okay, so I'll write that down more explicitly. In other words, Schwartz writes the field as integral dqp 2 pi cubed root 2et, and now AP of t e to the minus I px plus a dagger p of t e to the I px. Okay. So in other words, if this were purely a free field, then there'd be no t here at all. Because the t dependence of the field is just in these exponentials. And this px here is ep t minus p dot x. Okay, that's what I mean by p dot x here. So the free field time dependence is in the exponentials. The t here refers to the mysterious time dependence that occurs in the scattering. All right, so that's the time dependence here. And in particular, what that means is that A dot P is 0 if T is bigger than big T. So for large times, there's no time dependence at all. All right. So the key identity that we want to derive, maybe there's room to write it down here. It's I integral d fourth x e to the I px box plus m squared phi of x equals square root of 2ep times AP big T minus AP minus big T. So the difference in the annihilation operator times this kinematic factor is this huge integral, whereby the big T and the minus T, we mean the non-trivial time dependence, not just the crazy phase factor. And in fact, if we'd have trouble writing this if we included the free field time dependence, because this would be sort of e to the I, or plus or minus I, EP times in plus infinity or minus infinity for the time, so that the thing is spinning like crazy. Wouldn't make any sense. All right, so now let's imagine that the fields are weighted by wave packets, so that what we actually have is, a beam of particles, another beam of particles. They collide, and then they eventually form outgoing particles that, in any particular instant, are little itty-bitty particles moving in specific directions. And because we imagine that we've got these wave packets, those wave packets will fall to zero as we go to spatial infinity, so we're going to be able to integrate by parts derivatives in the spatial direction. There was a book written back in the 60s by two people, I think they were both in California, Livermore or Berkeley or somewhere, where they really put in the wave packets in almost every calculation. That gave people who were worried about wave packets, made everybody feel much calmer, because they showed that you could really carry out the wave packets, whereas other people were just saying, think wave packets, but I'm not going to use them. Sort of like someone in a police station who says, I don't want to speak until my attorney is present. So here it was, trust me or I'll call in my wave packet. That's basically the end.
Sorry.
Which is okay.
Sorry.
All right, so now let's carry this out.
Question.
Was there a question?
Yeah.
Yeah.
The 8p dagger in the 8p dagger goes away thanks to the m squared, right? No, I mean
8.
when we yeah, in that one.
Here.
Yeah.
This is the time derivative squared minus gradient squared acting on phi.
Yeah. And that's equal to AP minus AP.
The field is this thing here, and so there are two time dependencies. There's a time dependence due to the interaction, and then there's the free field time dependence, which is here.
Yeah, I mean, the AP dagger, how can that go away in the interval, in the second interval?
Oh, you mean why didn't this
Yeah.
appear here?
Yeah.
We'll see when we do the derivation. You have to be a little patient with me. Okay. But you can keep your candle. D4 x, EIPX, box plus m squared. And notice there's just one field here for simplicity, so we always talk about the same mass. All right, well, obviously this is what we just said, integral d4 of x, e to the I px, dt squared minus Laplacian plus m squared 5x. Okay. Now, we said now that we're going to call in our wave packets, and since we're all lawyered up, we can do the integration by parts. The gradients hit this term, bring down a minus p squared. or minus, well, they bring down a minus IP, but twice, so it's minus p squared. And so we have then a p squared here. And
So this is I integral d4 of x e to the I px dt squared, and this is plus p squared plus m squared 5x. All right.
And of course, that's just EP squared. So this is I integral d4 of x e to the I px dt squared plus EP squared 5x. Or one could call it omega sub p. I think that may be what Schwartz uses. All right, now we're going to show what this is in a slightly different way. In fact, I might be able to go backwards. I'm going to go backwards in my notes here. I'm going to rewrite this as, well, maybe it's better to go forwards. All right, here's what Schwartz does. He says d by dt of e to the I px I d by dt plus ep on 5x. Now you can manipulate this. The d by dt can hit this, or it can go forward and couple with this and this, getting ready to act on the phi. And so this gives us IEP, e to the I px, and then it's times I dt plus ep phi of x, plus e to the I px I d by dt squared plus ep dt phi of x. So those are the two things that happen. Yeah.
That's not equal to the previous line, is it? What you just wrote?
No, I'm not going from there. There's no equal
Okay.
sign. We're starting a new
Just making
calculation here,
Okay.
and what we're gonna do is we're gonna identify what's inside the integrand with what we get here.
Whoa! Good thing I liked it.
Okay, so some of these things, let's see, a little bit, some of these things cancel. Namely, this term is minus EP d by dt times the phase factor acting on that. On the other hand, this term is the phase factor EP d by dt acting on that. So they cancel. And so what we've got here actually is I e to the I px d by dt squared plus ep squared acting on phi of x. In other words, it's this term and that term. Okay. But all of this is what's in here. So the thing we started with, using this, is actually, we can say that this is integral d fourth x, an overall d by dt of e to the I px, and that's Lorentz product, I d by dt plus ep, and then phi of x. So using this little trick here, we see that this thing here, in other words, that's why I said I was going to go backwards. It's that this thing is this thing, which is the same as that. But now what we have is a total derivative. And of course, the two things I like best are delta functions and total derivatives, because either way, You get to do an integral cheaply. And so this gives us the integral at large times minus the integral at early times. So this thing then is, so if we sort of skip all of this, I can say that this is equal to the integral d cubed x e to the I px I d by dt plus EP phi of x, and we can say sort of in the lingo of calculus it's t minus t. In other words, at positive times minus at super negative times. So this is, the universe is cold and dark. He's way back before the CMB. Exaggerating. All right, now what do these integrals look like at these times? So let's just compute them. Integral d cubed x, which I think I'm going too fast, so feel super free to ask questions. E to the minus I p dot x. I d by dt plus EP phi of x. And we're going to be imagining this either at late times or early times. This is then integral d cubed x e to the minus I p dot x I d by dt plus EP. And now integral d, the expression for the field, which is on that fourth there, 2 pi cubed, 2 ek. Now we're going to have ak e to the minus I kx plus ak dagger e to the I kx. These are the Lorentz inner products. Okay. Well, what happens is that this I d by dt pulls down ek here, and it pulls down minus ek there. And so what we get is integral d cubed k 2 pi cubed d cubed x, and we get ek plus ep, that's the ep, over square root of 2 ek times ak e to the, and now we have minus I kx minus I p dot x. So this is Lorentz, this is 3 vector. And then over here we get something similar, except that we have an I, and so that's a minus 1. So we get minus ek plus this ep over root 2 ek. This is a square root of 2 ek. Sorry about that. AK dagger e to the I kx minus I p dot x. Well, p dot x is 3 vector and it comes in there, and I'm missing right parenthesis. All right, well, once again, Dirac to the rescue. You've got a complicated integral. The d cubed x over 2 pi cubed gives us, with this phase factor, delta of p minus k, the 3 vectors, and you see the k dot x comes into the minus sign here. And then over here, you would actually say k is going in the, actually that gives you the k in the minus direction, doesn't it? All right, so let's just see what we've got. So what we've got then is, the first one here says just p is equal to k, so this is AP, and this is 2EP divided by root 2EP, so this is square root of 2EP, AP at big time, so I'm doing this at t and then minus t. So that's at t. Oh, what I was worried about here, forget about it, because you say 3k is equal to the 3 momenta of k is the same as the 3 momentum of p, and so these guys cancel 0. So that guy is gone, and what do we have left here? We have e to the minus I ekt, or ept. So that's at plus time, and then we subtract at minus time, and at minus time, well, we just get this at minus time, so it's minus AP and minus T, e to the minus I EPT. So I could have factored out the, oh, wait a minute, that might be a plus. All right, so let me see, the EPs are canceling. So let me see what I got. All right, now I'm just a little bit. Oh, I left this guy out. Okay.
That's a 3 factor.
So in other words, I have the minus I. Oh, this is just.
Effective 2.
Okay, this is actually a 4 momentum, and I left out the T part. Okay, so let's. All right, at plus T, what you've got is e to the I big T, e to the I EP big T. That cancels this. So this never appeared. And then what you actually have is the phase factor cancels also at negative times. And
That's it.
yeah, it cancels just because these guys cancel. All right. Okay, so that's the marvelous formula, and maybe I should write it down with a fresh piece of chalk on the back wall there.
We have I equal p4 of x, e to the I px, box plus m squared, phi of x, and what we find is that this is square root of 2p times AP at huge positive times minus AP at huge negative times. All right, and if we take the adjoint of that equation, well, we get a minus I here, and remember the phase factors had opposite signs. Phi is Hermitian, these guys don't change. You get a minus sign here, but I'm going to use that minus sign to flip this. In other words, to make it AP of minus T. So in other words, I'm going to get I integral d4 of x e to the minus I px box plus m squared phi of x equals square root of 2EP a dagger p of minus t minus a dagger p plus t. Now, all right, so, right, okay, so that must be right. Yeah, it's exactly what we want. Okay, so what we want here is FSI equals, and of course it's the square root of 2e1 dot 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 2en, and then omega a sub p3 big T AP4 big T dot 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 APN big T a dagger P1 minus T a dagger P2 minus T interacting vacuum. So that's what we want. And well, there's a notice the thing is time ordered, so nothing can stop me from writing this, putting in a time ordered symbol explicitly. All right. Now, remember we said that none of the final state momenta coincided with any of the two initial state momenta. So we can replace every final state AP of T with minus, with the difference between that and minus AP of minus T. Suppose we do that. So then this thing looks like this. It's equal to square root of 2e1, 2en, omega big T, and now we've got A3 of T minus, I'm just going to suppress the p's, okay? I'll just call it A3. A3 of minus T, A4 of T minus, A4 of minus T, dot, 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 a n of T minus, a n of minus T, dot, 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 and then this one is going to be a dagger 1 minus a dagger, well, a dagger 1, I need an eraser, hold on. A dagger 1 of T minus a dagger 1 of minus T minus a dagger 2 of T, no, minus T minus a dagger 2 of T. All right, so I've done something, and you might say, well, how does he get away with this equal sign here? Well, the reason is that the time ordering says, oh, this one is at time minus big T, so he goes to the end of the line, but at the end of the line, the annihilation operator annihilates the vacuum. Similarly, we've got, say, an A2 dagger at T, the time ordering says, oops, this guy goes to the front of the line. Ah! God, you got big. Jesus Christ. I mean, I've seen elephants with small. All right, so A2 dagger goes to the front of the line and it annihilates the vacuum. By the way, there's a typo in Schwartz. He says it annihilates the initial or final state. It doesn't do that. It annihilates the vacuum. So this is actually true. And now we can replace these square root of e's and the differences of the operators with these things. And so altogether we get omega, time-ordered product, I, product of final states, integral d4th x, well, put the I in. Let me get the right ones. Yeah, e to the I, px, box plus m squared. M squared. And I'm going to put the phi's later, just, and time ordering will fix everything. Product of the initial states, I integral e
d4 x minus I px, and it should be j, and let us say k, and box plus m squared k, and time ordered product, and phi of x1, phi of xn, n time ordering vacuum. Okay. So, what we do now is something that's not really legal. We're going to pull all the differential operators out to the left. And there's no problem with that, except that we have time derivatives here, and this is a time-ordered product. And so a time-ordered product is something that's a sum of things times products of theta functions of time. And so it's not really legitimate to do the following, or do what I'm about to do. But on the other hand, the errors that this operation introduces just introduce what are called contact terms, and they don't affect the S matrix. We'll be talking about them in a later chapter. So the final thing then is that this is product over the final states, I integral d4 of xj, e to the I, pj, xj, box j plus m squared, product over the initial states, I, d4 of x, e, minus I, pk, xk, box plus m squared, and now vacuum time ordered product phi 1, phi of x1 say, phi of xn vacuum. Okay, so that's basically the picture. In other words, the S matrix element is an integral of these operations, which are Lorentzian product as the phase, and I, integrate over all space. You have a minus I here, box plus m squared, and then a Green's function. So that's basically, that's the Lehmann, Zemancic, Zimmerman reduction formula. And I've of course done it for scale fields, so you can do it for arbitrary fields. And when they actually presented this, they weren't thinking so much, they weren't trying to make it as simple as possible. They were trying to make it as general as possible. And so they were talking not about free fields. Well, we weren't talking about free fields either, but they were, in other words, you can generalize this to any operators that do the following. So let us say this. Whoops, I wrote phi, I meant just some O. So O of X, vacuum P, in other words, state of momentum P, as long as this is some factor Z times e to the IPX. In other words, when O hits the physical vacuum, it makes one particle state plus other stuff. So the action of O on the vacuum has some overlap with the one particle state. The overlap is Z. Then you can write the same formula, except you get a bunch of 1 over z's, I guess, and you can put your O's down here. So it's more, so the LSE formula is actually more general. And let me just mention to you why it is that if O is a scalar field, why it is that you'd expect that you get on the right-hand side this, where Z, of course, could be 0, but you've got to get this factor. And the reason for that is that O of x is actually P e to the I px O of 0 e to the minus I px vacuum, where P is the actual full momentum operator, which produces translations when it's exponentiated. On the other hand, P on the vacuum gives you 0 because the vacuum presumably has no momentum or energy. We're ignoring dark energy here. This one hits that and gives us e to the I px, where that's the momentum there. And so then we have P O of 0 omega, and that's the thing we're calling Z. All right. Okay. And for some reason, Schwartz then says, well, this O, we could write it in terms of sums of products of annihilation, creation operators, integrated over momentum, and that's fine. I don't think I'm going to write that down. All right, the next topic is the Feynman propagator. We might be able to get through that. I wish I had a joke, but I can't think of one. All right, now this Feynman propagator is basically, actually I think Schwartz's treatment of Feynman propagator is quite nice. Once again, he makes it as simple as possible, and in this case, not simpler. Phi of x, of course, is d cubed k, 2 pi cubed, 2ek, ak e to the minus I kx plus ak dagger e to the I kx, and these are the Lorentzian products. Ek is the on-shell energy, in other words, it's the square root of m squared plus momentum squared. All right. So let's consider vacuum, and we're thinking of this now as a free field, so we use the ordinary vacuum. Phi of x1, phi of x2, ordinary vacuum. Well, what happens? Well, you need to create, the first one only contributes an annihilation operator, the second one only contributes a creation operator. So this is d cubed k1, d cubed k2, 2 pi to the 6, square root of 2ek1, 2ek2, vacuum ak1, a dagger k2, vacuum e to the minus I k1 x1 plus I k2 x2. All right, so that's what we've got. Now, we know that the commutation relation is AP a dagger cubed 2 pi cubed delta p minus q. So, we have a delta of k1 minus k2, 3 vector k. And that means that one of these k's has to be the same as the other. Then the two energies have to be the same. And so this turns out to be integral d cubed k 2 pi cubed 2ek e to the ik x2 minus x1. This is Lorentz still. All right, are we happy? And the k here I chose to be k2, so I absorbed k1. All right, so we're happy with that, are we? All right. So, what about the time-ordered product? Well, the time-ordered product would be, it would be this times theta of T1 minus T2 plus this with x1 and x2 interchange times theta of t2 minus t1. So in other words, vacuum time ordered product phi of x1, phi of x2, vacuum. Now this is another Green's function. It's a Green's function for a free scalar field, and this is what's called the Feynman propagator. So what is it? Well, it's of course 0, phi of x1, phi of x2, theta of t1 minus t2, plus phi of x2, phi of x1, theta of t2 minus t1. Vacuum. And of course you can stick a vacuum on the right here and a vacuum on the left there. All right, well we know what these are individually. And so this is equal to integral d cubed k, 2 pi cubed, 2 ek. Why 2 ek? Because we had a 2 ek over here, not a square root. And then the first one was x1 minus x2. That's the thing we computed there. So that was e to the ik x2 minus x1, and this is Lorentz, and this is theta of t1 minus t2. And then we get e to the ik x1 minus x2, theta of t2 minus t1. Okay. And we're going to let tau equal to t1 minus t2. All right. So if we do that, then what we get is integral d cubed k, 2 pi cubed, 2 ek. And then we get e to the minus I ek tau minus I k dot x2 minus x1, and this is 3 vector, and this is theta of tau. And then the next term is e to the I ek tau, e to the minus I k dot x1 minus x2. All right. Times theta of minus 4. Okay. All right. So, what do? We want to combine these a little bit. And so what we do is in the first integral, we flip 3 vector k to minus 3 vector k. Well, that doesn't care, that doesn't care, this doesn't care. So, we can just do it, all right? Now, we've got these two guys are the same, and we just have the e's different. And so what we've got now is integral d cubed k, 2 pi cubed, 2 ek, e to the minus I k dot x1 minus x2. So that was this one. And then we have e to the I ek tau theta of minus tau. That's the second term. Plus e to the minus I ek tau theta of tau. All right. Now, what we're going to do is we're going to
rewrite the square brackets as a contour interval. Okay. Let me see if I can. I know what I'm going to do. Use wet eraser here. And because this is New Mexico, this will be dry in a moment. All right, does anybody have a question?
Yes, why do we need this time ordered product?
Why do we need the time ordered product? Well, you see, time ordering came in a natural way. Here, I have to give you two, don't I? Time ordering came in a natural way in the very beginning. So we started out by saying, well, I put it in there, but the time ordering, I guess, is that we need the time ordering basically to move the initial state operators to minus times and the final state operators to later times. That's basically what the role of time ordering is.
So why don't we just move them by hand?
You're saying, why don't we just do the thing? All right, let's look at it. What would happen? I think we have time to work this out. What would happen if we did what you're saying and we just said, well, we're going to use these two relations. We're not going to do time ordering. Well, you see, the trouble would be that we wouldn't have time ordering here. We'd have A3 of t minus A3 of minus t. And that would just be sitting there. And so would all these. So this thing would look like this, and we couldn't get rid of this operator, we couldn't get rid of this term, and we couldn't get rid of this term or this term or that term. They'd all still be there. And so, you know, we just have a very complicated expression that wouldn't just be our scattering, our S matrix element.
And we did it wrong.
Hmm?
Well, so if you can't do it with time ordering, then you did it wrong, right?
No, we use time ordering.
Oh, just to move it, okay.
I mean, the only thing we did that was a little illegitimate was pulling the time derivatives here through the time ordering so that we yanked them out, so we just had the time ordering on the fields. But the time ordering, basically, what it's doing is it's putting the initial state stuff on one end and the final state stuff at the other end. I mean, it's natural that you've got a time order. All right, now let's see what we can do with this. And so it's still damp, but I'll shoot it go. E to the minus I ek tau, theta of tau. So I'm going to try to prove this, and oh, this is a plus sign. Plus e to the I ek tau theta of minus tau. We want to say that this is going to be a limit epsilon going to 0, minus 2ek over 2 pi I, and now an integral minus infinity to plus infinity e to the I omega tor over omega squared minus ek squared plus I epsilon d omega. All right. This I epsilon is the famous I epsilon in the Feynman propagator. And why is that equal to that? Well, it's just this contour integral. So what do? The first thing is we just sort of rewrite it, and we say it's minus 2 ek 2 pi I integral minus infinity plus infinity e to the I omega tor d omega, and now we factorize that, and let's notice the way we factorize it. Omega minus ek minus I epsilon omega minus ek plus I epsilon. Okay, now why is this okay? Well, if you multiply that out and look at the terms that are linear in epsilon, the linear in epsilon terms are 2I epsilon ek. But ek is positive, and so we imagine, we think of 2 epsilon ek as a small positive number, and the epsilon squared term we just ignore. Okay, so what do? Well, we've got a pole here, and we've got a pole there. And if tor is positive, if tor greater than 0, well, if tor is positive, then what we want is we want omega to have a positive imaginary part, because then this will be exponentially small. So we can add what I like to call a ghost contour that goes over the North Pole. And where's the pole? Well, it's this pole, so it's over here. And it's a ghost contour because it's really 0. So now we do the case tor positive. We add the ghost contour, and this is a contour around this point, and so this gives us minus 2 ek. There's the 2 pi I, and then there's the e to the I tor ek. In other words, omega gets replaced by wait a minute, I wanted to say minus ek. Oh no, now I'm confused. Oh, I was on the wrong line. Minus ek, yes, that's the minus ek. And then we divide by this thing, evaluated omega to minus ek, and that's just minus 2 ek. So this thing is simply e to the minus I tor ek for tor positive. So this gives us effectively theta of tor. If tor is negative, then we add a ghost contour like that, and we pick up this guy where the pole is there, but now we're going clockwise, and we get a minus sign. So altogether now we get minus 2 ek, e to the I tor ek, that's this term. Then we have a minus 1, and we have to divide by 2 ek, which is whatever's left. Let me see, I keep getting confused here. This pole here is this one, and consequently these two guys come in with 2ek. All right, so altogether, this one turns out to be e to the I tau ek, and now this is theta of minus tau. So you see, either minus I ek tau, I've got it backwards, don't I? No, this one plus that one. Okay, so we wound up with the correct form by this contour integral. Oh, I'm a couple of seconds over. Well, here, let me just finish it by saying that this thing is the extra contour integral. So this is an integral d omega t cubed k 2 pi to the 4th I, and now we have what we can do is we can again flip the sign of the 3 vectors. The 3 component here doesn't really matter, and so well. Oh, it doesn't matter, we've already got this. Because this thing here was, you see, this e to the I omega t. So this is an e to the I omega, omega tau, wasn't it? That's right, e to the I omega tau minus I k dot x1 minus x2. And then what's in the denominator is, it turns out to be k squared minus m squared plus I epsilon. And so, pulling up the I, and there's a minus I. And so the whole thing is d4th k, 2 pi to the 4th, k squared minus m squared plus I epsilon, e to the I k, x1 minus x2, and that's the Lorentz product. Well, I think what I'm going to do next time is I'll redo the last few minutes of this, because I think it was a little too fast, and it was a little sloppy, so I'll redo that. Okay, any questions?